Hi everyone, and today we're looking at polymer chemistry. So polymers are long chains of molecules. They can be hundreds of carbons long, they can be thousands of carbons long, tens of thousands of carbons long. So they are huge, huge molecules that are made from repeating units called monomers. So monomers are usually, they can be anywhere from like 2 to 4 carbons or bigger, but they're small repeating subunits of a polymer. So when we see a polymer chain, we see a lot of repetition, and this repetition comes from those monomers. So polymerization is the process by which monomers become polymers, and polymers can be two different types. They can be synthetic, so human-made, or they can be natural, meaning found in nature from plants and animals. So think about which polymers can be found in this room. Are they synthetic or are they natural? So wherever you are right now, if you're somewhere in your home or even outside, there's polymers all around you. You are probably wearing some polymers. You might be using some polymers to watch this video. In fact, for sure you're using some polymers to watch this video. So we're going to learn a little bit more about those today. So we're going to look at some reactions that we use to make polymers, and the first one is called an addition reaction. We're going to look more about reactions after this section on polymers, and you're going to see there's similarity between these types of addition reactions and the ones that we see later. So when we do addition reactions, we have to have monomers, these small units. They must have a C double bond C in them, because we're going to make use of the fact that C double bonds are pretty unstable and that it doesn't take much to open them up. And when we open up one, it actually sets off a chain reaction, like a domino effect, that opens up all of the other ones, and then they can attach to one another into this big long chain. So these are how we actually make most plastics. So if you think of plastics, there's lots of different types. If you go in and around your home and look at the different types of plastics you might find in your kitchen or in your bathroom or anywhere in your house, they're not all the same, but they all have similar qualities that we're going to look at as well. So let's see how this might work. So this is an example of 3 different monomers. I want you to notice a couple of different things. First, I want you to notice that there's some dots on either side. That just means that we're taking 3 monomers of typically what's more like thousands of monomers. So we're just showing a very small cross section of the monomers that would make a very small piece of this polymer that we're going to show. This part should just be an arrow. Again, this program doesn't always convert nicely, so let's make that an arrow. There we go. And what happens with a polymer, we usually have a bunch of monomers sitting around doing nothing, and then we send in a material, something that's active, that breaks open the first double bond. And so we break open that double bond, and you can think of it as sort of like this trap door where 1/2 goes this way and 1/2 goes this way. And that starts off a domino effect in which all of the double bonds are broken. So when we show the polymer, if you have a look, we have 6 carbons in total. We're going to show 6 carbons. 1, 2, 3, 4, 5, 6. We're going to show those dots on either side because, again, this is a small part of a really, really huge chain. And the H's are still there, but what has happened is these are the H's here, top and bottom, just like we showed them above. But what we've done is we've taken the inside double bond, and think of it like folding your hands across your chest and then opening your arms out to the side and grabbing onto your neighbor who just did the same thing. That's essentially what's happening. And we actually I usually do a human demo where I have a bunch of people that are doubly bonded, and we break you open and you become singly bonded. So essentially, like I said, if you were considering grabbing your hands in front of your body and then opening that up and grabbing onto partners on your left and right, that's essentially what's happening here. So all of the stuff that's hanging on the carbons in the monomers is the same stuff that's hanging on the polymer. That part doesn't change. We're just going to connect them by breaking the double bonds and then extending those bonds between the monomers to create that polymer chain. We can also go the other way around, and this picture has really shifted on me, but I'll redraw it on the next slide. So we're going to go backwards this time. We're going to look at this polymer, which is a little disorganized looking. We're going to go back and show the monomer that it was made from. So I've just redrawn the polymer for us, and everything's a little more organized now, although it seems to be getting bigger as I go from left to right. I don't know. It's a perspective thing, people. It's coming towards us. Anywho, So when we're looking at how do we break this up into the monomers, you're looking for repetition. So as I go from left to right, I notice along the top there's a Cl, then an H, a Cl, then an H. So every time there's a repetition, that's actually where the monomer is. And now what I'm doing is I'm going to take those bonds that are stretched out on either side and I'm just going to bring them back in. So I don't actually have to show this, but I'm just kind of trying to give you an idea of what I'm actually doing. So I'm going to pull the extra bonds back together and I'm going to create my monomers. So my monomers are going to have a Cl and 3 H's. And typically we draw 3 of them because the idea is that however many carbons we show in the polymer, we also show the same number of monomers. So if I have a polymer showing just 6 H's, I show monomers that represent those 6 H's, or sorry, C's rather. So again, I put dot dot dots to show you that there's many more monomers than this. And again, I'm only showing a very small piece of this puzzle. Again, it's trickier than it looks with all these red arrows. Don't even worry about those really. But all we're doing is we're just pulling in the bonds that connect the monomers and putting them back into their double bond form as monomers. So on this side we have our monomers. And again, this is usually thousands. We're only showing 3. And then this is a long polymer chain. Again, we're only showing 6 carbons in what's probably thousands of carbons big. So the substituents that are on the monomers are the same as the polymer as we see, and polymer chains are held together through intermolecular forces. And so the stronger or in terms of how many intermolecular forces a polymer chain has, the stronger it's going to end up being. So think about it like this. If you have a plastic container, think about these polymer chains as being just stacked on top of one another. The plastic container isn't one string that's wrapped around itself a million times. It's multiple strings that are all just hanging out together, and they're only attracted and keeping their shape because of intermolecular forces. So we know that the intermolecular forces could be London, they could be dipole-dipole, they could be hydrogen bonding, and we know that the strength is determined by lots of different things here. So the main intermolecular force that most things actually have is actually just London forces, because a lot of plastics are just carbons and hydrogens, believe it or not. And normally, as we know, London forces are really weak because there's, not a lot of attraction between protons and electrons of neighboring elements. But because the size of a polymer is so huge, London forces are actually really big. So you can have a plastic bag, for instance. A plastic bag is only carbon chains and hydrogens. So all you have attracting is London forces. But that attraction is so strong because you have so many protons attracting so many electrons that you can put lots of stuff in a plastic bag before it breaks. So London forces have actually become really, really strong all of a sudden. How could we strengthen a polymer chain though? So if we want to improve our intermolecular forces, what are some of our methods of doing that? Well, for instance, we could do things like change the H's. So instead of an H on our carbon, so instead of just H's here on our carbon chain, what if we change them into something with a polar bond? So like an OH group. Now all of a sudden we have 2 things. We have now added dipole-dipole attraction, and we've added some hydrogen bonding attraction between our chains. So by changing the functional group, we can improve our intermolecular forces and therefore strengthen the overall strength of the polymer. If we think about plastics, we use them for so many things in our lives, and they become such an important invention because of the following properties. Now, of course, the properties that make them so great also make them so destructive. So let's talk about them. The first thing is that plastics are unreactive. Because we take double bonds, which generally aren't very stable because you have 4 electrons in a small space and they're all repelling each other, versus 2 electrons working together for stability, single bonds are really unreactive. So you can put things like food and water in them, and it doesn't get into our food and water when we drink it or eat it. They're generally insoluble. So You know, you can fill a water bottle with water and the water bottle doesn't dissolve on you. That'd be a terrible water bottle. They're flexible and moldable, so we can put them into different shapes. We can get them to take on all sorts of shapes. We can make phone cases out of them. We can make plates out of them. The intermolecular forces are holding our chains together, but they can slide across one another. So if I have a bunch of chains like this, because only intermolecular forces are holding them, I can pull the plastic bag or whatever piece of plastic I'm working with, and I can bend it and stretch it, and that's part of why I like plastics for certain things. Sometimes I want that flexibility, and because it's only held by intermolecular forces, we get that flexibility. Heating also increases its flexibility because the particles are now moving faster, they're more mobile, and therefore that makes them more flexible and moldable. Now, if we were to sit on a plastic bag, it probably wouldn't take long before we fell through it. So intermolecular forces are awesome, and they're really strong typically in a polymer chain, even just London forces. But when we think about really strong intermolecular forces, even the strongest ones really can't hold us up. Like, think about water. It's got all three intermolecular forces, but we can't stand on water, as far as I know. So how is a chair holding me up right now? Now, I'm not sitting on a chair. I'm in my closet. It's very sad. I'm sitting on a pillow, but I was sitting on a chair earlier. And how does a plastic chair hold me up? It has to be more than just intermolecular forces. Yes, there is. We can improve the strength of polymers by introducing a topic called cross-linking. Cross-linking is where we actually create an actual covalent bond between the chains. So instead of just loose chains that can be stretched and very flexible and move past each other very easily, we can actually create a link, thus the name cross-linking, of an actual physical bond between them, and that creates a whole lot more strength. What we need to do this is we need something that's a diene. So we need two double bonds. We need an extra double bond. So what ends up happening, you can see some examples on page 105, but I'll show you an example too. So I'm going to keep the substituents out of it just to keep it more clean. But let's say that this is a row of monomers getting ready to make a polymer chain. I've got my dots here because they are continuing in a large fashion. This one is a very special diene monomer. And so you can see here that it's got a second bonded double bond down at the bottom. So what happens here is I can get that double bond to be part of a second group of monomers. I'm going to put them in gray. Again, dot, dot, dot. So now I'm going to stimulate the reaction to open up my bonds, and I'm going to do the top part first. So it's going to go like this. 1, 2, 3, 4, 5, 6, dot, 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 dot. And then the third carbon had that extra carbon chain. I'm going to open up the second row now and join them. So again, we put that special ingredient. Here we go. Dot, dot, dot. And now the two monomer chains are now physically connected because the diene became part of two chains at the same time. So if we think about these chains, here they are like little spaghettis here. Normally all they have is intermolecular forces holding them together, so if I were to pull them apart, they would slide easily and be very flexible. But all of a sudden, if I put a cross-link in, I have a lot less mobility. So when I'm doing cross-linking, when I want to make a really strong polymer, I put a bunch of these dienes in. Not as many as the regular monomers, there's mostly regular monomers, but I put enough in so that every now and again you get these little cross-links. And therefore we create a much stronger situation. I can't pull in any of the directions now because I have physical covalent bonds keeping the polymers from moving apart from one another. So if I want a really rigid and strong polymer, cross-linking is the answer. This is just an example from your textbook with styrene. Styrene is the monomer for polystyrene, and polystyrene is how we make styrofoam. Now, styrofoam isn't particularly strong, but it's a lot stronger than it would be without cross-linking. So again, this is the regular monomer, This is the special diene monomer, so you've got the two double bonds here. So you'll notice that the two double bond one has been used right here. So we've got the first monomer chain and the second monomer chain making polymers, and the crosslink has been created right here, which tells me this must have been my diene. Now the reason why this doesn't create a ton of strength for styrofoam is because these giant benzene rings that you can see all over the place create huge gaps between the rows of polymer. So if you think of most polymer chains, I've sort of been drawing them like this. Styrofoam would be more like this. And that's why styrofoam is so light, because there's lots of air that gets in between. It's giant pockets, and so it's very light. The polymer chains can't actually physically get that close to one another because of these giant benzene rings getting in the way. So the polymer requires some cross-linking, otherwise there's just too much space and it really wouldn't hold together. So that's another reason why it would get cross-linking. So it is improving strength, but we don't really think of it as being strong like a typical plastic. So the second type of polymer is called a condensation polymer, and these have to have reactive functional groups on each end of the monomer. So often we have two totally different monomers here, whereas with our addition monomers we usually have the same one over and over. We can also have one monomer with two different functional groups on its ends. So there's a couple of different ways we can make a condensation polymer, and I'll show you both of them. And these things tend to make fabrics. So thinking about polyester, nylon, there's all kinds of them. If you look at the labels on your clothes, you will find condensation polymers. So let's have a look at polyester. If we think of the word ester, and ester is a C double bond O and an O. So that's our functional group there. This functional group is going to come from two different sources. And again, we're going to do some types of reactions after this, and you'll see that this reaction is very classic. So there's two different parts. There's this part of the O and that part of the O. So it requires a couple of different types of functional groups to be put together to make this type of thing. This one's definitely a little more complicated, and again, when we do some single-step reactions, we'll see this one again, only it'll be single-sided instead of double-sided. What's happening here, and if I had more space, I would do a couple more of these monomers for us, but we have a carboxylic acid monomer over on this side and on this side, and then we have a second monomer that's just an alcohol, but a double-sided alcohol. And this is called a condensation because condensation means remove water. So the way we get these two chains to stick together to become a polymer is right in between them we remove water. We remove an HOH. So I'm going to take the OH part from the carboxylic acid half and the H from this half. I'm just going to pull it off. What I'm going to do now is I'm going to push these two chains together. The same thing would happen on the other ends. So on this end with an alcohol, with its neighboring alcohol, it would be pulled off. Same thing with this guy. He would be pulled off with his neighbor as well. Again, I've only drawn two, but if I were to draw 4 or even 6, it would be a little bit easier to see. So what would happen then? Here's what my polymer would look like. The OH would come off and be a partner, so I would just start the process here. CH2, C double bond O. Where the yellow is, that's the water that I've pulled off. That's going to be a second product. And because it's gone, I'm going to connect what's left. So I have a C double bond O on the left, and on the right, I have this O from the alcohol. And then again, I have another O, and then that H presumably would be pulled off and going with its neighboring functional group. So I would make this plus some water, and that's how I would make that. So polyesters can be lots of different things. They just have to have these two functional groups. So we can like I said, it just means condensation means to remove water and push the groups together. So we do that between the two functional groups, and that's what we make. You can do the same process with one type of monomer with different functional groups on both ends. All right, this one might be a little bit easier to see because I was able to draw more of them in. So again, we're going to take out the water in between. So for each section, I'm going to take the OH of the carboxylic acid and the H from the alcohol and pull it off. And I'm just going to keep doing that for each partner. And I'll just sort of assume that it's going to continue in both directions here. So again, every time I pull that water out, I'm going to push the leftovers together. So my product ends up looking like C double bond O, CH2, O, and then I'm going to jump across the water to connect the next part. And then I'm going to jump across the water to connect the next part. And I'll leave it there, dot, dot, dot. And then my water will be separate. So that's how I can make the same type of thing with one type of repeating monomer. And this monomer just has both functional groups on one monomer instead of two different monomers with difunctional groups. So you're going to try some homework, and we're going to have a little mini project on polymers that you're going to work on starting tomorrow. You'll have some more time next week to do a little bit of work on that, and some also a worksheet to practice. So you have lots of time to get your head around polymers.